So let me start by sharing the screen, and we can have a little recap of what we saw yesterday and the day before. Let's quickly recap. So we introduced these, what we called integration by parts identities, which in the end boil down to recursions in the exponents. And from that, you can get basis of integrals, Feynman integrals, which are often called master integrals. So for every family of integrals, by family I mean integrals that share the same propagators, or subset of propagators, you can associate this lattice, and then the IVPs give you recursions on this lattice, and you can find a basis, which is the master integrals. And then there's the question of how you compute the masters. And here, well, the IVPs were obtained from computing derivatives with respect to the loop momentum. Now, the idea is that if you compute derivatives with respect to external momenta, plus the IVPs, this gives you differential equations for the masters. And they will always be first order linear differential equations for the masters. So if I denote by I the vector of masters, so master integral 1 to master integral k, say we have k master integrals, then the total differential of I will be some matrix A, which will depend on some vector x, which is my kinematic quantities, the masses and the Mandelstam invariants, and their working dimensional regularization. So there's an epsilon times I. So that is the main idea. You can always find such a differential equation. And then we said, well, there's a conjecture which is satisfied in all examples we know, and those are many examples, that there is some algebraic matrix, some algebraic rotation you can do, such that if I define a new basis of master integrals, J, satisfies a differential equation of the type dj is equal to a1 of x plus epsilon a2 of x J. And this is very strong. And there was, in the discussion session yesterday afternoon, we looked a bit more into detail at this. The important thing here is that this matrix is algebraic. So the matrix A here is rational. This matrix is always rational. The non-trivial claim is that you can always make the dependence on epsilon linear, so simple, via an algebraic rotation. Algebraic means, say, the entries of this matrix are rational functions and square roots. That's what you get in practice. So the non-trivial part is that there is such a matrix M that is algebraic. So in practice, what is known is that A1 is often 0. And then this is often called the canonical form. Sometimes people also call the form with A1 0 canonical form. It depends on what you look at. When A1 is 0, then of course it's even simpler. And we said that then the basic idea is that you say, okay, well, my J, which depends on X and epsilon, I can write it as a path-ordered exponential of epsilon times, say, in start integration from point x0 to x times A2 x. This is a matrix. This is like a Wilson line along a path that goes from x0 to x. And you take the value of the function at the point x0, and you transport it along this path to the point x where you want to know the solution. And the basic idea was that since we work in dimensional realization and we want to know the expansion in epsilon, what you get is that, well, if you have this special form where you have only epsilon times a constant matrix, or constant with respect to epsilon, then computing the epsilon expansion is particularly easy, because it's just the exponential of something of the type epsilon times something exponential. Okay. And we looked here at the example where, well, that is called A tilde here is what they called A2 here. Where it has two terms, so A0 and A1 are really constant, also with respect to x. And well, then you just have to unfold the path of the exponential as you would do with perturbative expansion of a Wilson line in QCD, where there the matrices A0 and A1 would be, say, the generators of the Lie algebra. Epsilon would be the coupling constant, and the 1 over t and 1 over 1 plus t would be propagators, essentially. So it's essentially the same mathematical formula. Okay. So this sums up what we saw yesterday. Are there any questions about this?
Yes, I wanted to ask, I don't see any poles in epsilon in this expansion.
Correct. And clearly, if you expand the expansion of an exponential of epsilon times something, that quantity has no poles, clearly. But the actual solution for the integral is, you see, what the Feynman integral is the vector I. Right? That is the thing that you start from, which is related to J via this M, which also depends on epsilon, so that may have poles. Then on top of that, the J is given by this path-ordered exponential acting on the value of the J at some point x0, which again depends on epsilon, and that may have poles. So the poles are not in this path-ordered exponential. The poles are either an initial condition, which is J of x0, or in this additional rotation, this additional gauge transformation that they had to do to bring this system into canonical form.
But then, so the part that I don't understand is, let's say this initial condition, right?
Mm-hmm.
Let's say we're looking at a massless integral, right?
Yeah.
And then we're integrating up to a massive integral. So does that mean that massless integrals would always have the same poles at massive integrals?
No.
So where do because it seems to me that the initial condition has the same poles as the...
No, that is not correct, because there's two places where you get epsilons from, which is here and here. I mean, this quantity may even start at of the type where there may be zeros in epsilon. This may be proportional to epsilon. So even if this guy has a pole in epsilon, this guy may not, for example. Well, this guy may not.
Okay, I see. I see. So there's some pole information can be hidden away in the transformation as well.
I mean, there's some pole and zeros which are hidden in M
Uh-huh.
and in J, such that this thing is the identity matrix to leading order in epsilon.
Okay, I see.
If you want everything else, this normalization, let me put it like this. Imagine you have this. Okay? I could also say this is a normalization factor which is divergent times this.
Yeah.
This is just a stupid normalization factor.
Mm-hmm.
And that normalization factor, I may hide it in this M.
Yeah.
Okay? So what I call pole is a bit immaterial. It's just, I can pull it out and then hide it in M.
I see. Right. I did notice that. So then we would need this expansion of the exponential, of the order exponential, only up to the order of the poles of the initial condition, of the deepest pole of the initial condition.
No, well, no, you need it up to the order to which you, so that you know this I, which is the thing that you want, two sufficient orders in epsilon.
Yes.
The
Okay.
order to which you need the path ordered exponential, well, let's wait until the end of today's lecture. This will, there's a meaning to this expansion here, which you haven't seen yet. And then you will understand either at the end of today's lecture or in early tomorrow's lecture, you will see where you have to truncate.
Okay.
You can predict this, but at this point, it's not obvious. I haven't told you yet how to do that. At this point, the only thing you can say is, if you want to know your I, which is the integral you want to compute, or the set of integrals to compute, to a certain order in epsilon, you have to compute all the ingredients to sufficiently high orders so that makes sense. We will see that there's a more that you can predict the order to which you need to expand the path ordered exponential. Okay? More questions? We will also look at this in a minute on the example of the box. We'll even look at it from the point of view of like not writing it down, but you will see it in Mathematica is a bit cleaner even than if you just write it down. But before we do that, before we show you how this thing looks in practice, there's one thing that we haven't discussed yet, which is precisely the question of what happens to the initial condition. So how do I find it? The path ordered exponential we have discussed now. You have to find this canonical form. In the case where A1 is 0, you have computer codes that help you to do that. I'll list them here. But then once I have it, I still need to solve the initial, well, find the initial condition. So what about the initial condition? I mean, clearly, one approach you can take is, well, compute all the integrals at some point, x0. If you have that, then that's it. You just have j of x0, and then you parallel transport the solution to any other point you like. This you can do, always. Of course, it means that you have to evaluate the integral at some point, which can be very complicated. It can be easier than a full calculation. For example, as was just mentioned now, you may, for example, say, okay, know the integral at the point where, say, particles are massless, and I need to then use the differential equation to transport it to finite value of the mass. But even computing it, say, for massless particles could be extremely difficult. So that is why often you use something else. It turns out that often you don't need to compute any initial condition. The initial condition is part of the physics often. What do I mean by that? So remember that we said that these functions know about unitarity. There was this thing called the optical theorem. The optical theorem, which tells you that the discontinuities of an amplitude are related to, well, essentially the cuts of the amplitude. So there's physics, so particles going on shell. More precisely, you see from this that the only branch points, so the only points where you have a discontinuity, come from points where some Mandelstam invariants go to 0. Say, oh, if you have a massless particle, it would be points of Mandelstam invariants go to 0. In general, they would be thresholds. There would be thresholds in the amplitude. Say, points where particle can go on shell. If the external kinematics is such that internal particles can go on shell, then you develop an imaginary part. That's what unitarity tells you. And you can use that. You can use it in reverse, because you can say now, well, unitarity tells you that the only discontinuities, the only imaginary parts should come from situations where the external kinematics is such that internal particles can go on shell from thresholds. So let's look at it as an example. It's actually, from there, I think it should be very clear. So what does that mean, for example, for the box we want to compute? So the box depends on two invariants, S and T. And well, so there are two discontinuities you can consider. You can consider the cut in the S channel, where these two particles will be on shell. Or you could look at the cut in the T channel, where these two particles are on shell. So you see that there is no way I can kind of fold this thing up such that they're getting a discontinuity when U is equal to 0. So these two discontinuities would correspond to S equals 0, T equals 0. So those would be the points where I develop imaginary parts. But there's no way from quantum field theory I would get a discontinuity when U is equal to 0, because it's a planar graph. I cannot achieve that kinematically. I mean, you cannot even draw the corresponding cut diagram. Now, if you translate this from U to our variable sigma and x that we introduced yesterday, I remind you, sigma is essentially minus S, and x is T divided by S. So U is sigma times 1 plus x. So when would U be 0? U would be 0 when either sigma is 0, which is S equal to 0. So that would be the S channel discontinuity. That's okay. Or x is equal to minus 1. X equal to minus 1 would mean that S and T are non-zero, but U is 0. And we know from physics that there's no cut corresponding to U equals 0, so there should be no discontinuity when X is minus 1. No. However, if you go and you look at the general solution, which is what comes out of the path-ordered exponential, you would have a singularity at x equals minus 1. There would be a discontinuity associated to x equals minus 1. So for example, let's take the path-ordered exponential, and let's expand it to order epsilon. Now, I guess you can easily see that this integral just gives you a log x over x0. And this integral here gives you this. And you see that here you have this log of 1 plus x, which develops an imaginary part, well, which is singular when x is equal to minus 1, and develops an imaginary part when x becomes less than minus 1. So in the path-ordered exponential, in general, you will find imaginary parts that develop when x crosses the point minus 1. But those imaginary parts are not physical. They are not part of the physical structure of the integral. So the initial condition must be such that this log of 1 plus x is absent. Okay? So by using the fact that you know from physics what the singularity structure of the answer should be, in particular where the branch cuts should be, you get information on how to construct a special solution with the Feynman integral given the general solution. The general solution will always have all possible singularities that you have in your differential equation, because if the singularity is part of the differential equation, it is at least one solution that has the singularity. Otherwise, it wouldn't be there. So for the box, well, we'll see that this example of that we looked at here corresponds to the box. You see that there is, in general, the differential equation would show you that there are two singularities, one at x equals 0, one at x equals -1. So the general solution will have singularities and branch cuts associated to x equals 0 and x equals -1. The Feynman integral does not have the singularity at x equals -1, so this puts a constraint on the special solution that corresponds to the Feynman integral. Okay, so that is a way to fix initial conditions. Of course, if you manage to evaluate the integral at some point, that is very good and very well. There's nothing nothing wrong with it. But often knowing it at one point can be very difficult, while using physical input as initial condition can be much more efficient. Okay, is that idea clear? So this was lots of abstract talking. So let's maybe look at an example. So you should now see some Mathematica notebook. And I'll guide you through it. It's so I load here. This is a package which was written by Roman Lee, which allows you to give the propagators, and then it solves you the IVPs, and it can derive the differential equations and so on. So it just implements all of these, the mechanics related to these integration by parts. So the first thing I need to do is I need to just define the integral, and let's do this box integral. So, okay, I have to tell the code what is the space-time dimension. I keep it general, D. And I have to say, okay, what are the symbols that I need to use? So there's K, which is will be my loop momentum, and P1, P2, P3 will be my external vectors, and S and T will be the Mandelstam invariants of Gen numbers. This is just declaring the variables. And I can also define the kinematics, in particular, all possible dot products between external momenta. So my box was completely massless. So P1 square is 0, P2 square is 0, P3 square is 0. So SP of AB is the dot product between A and B. P1 dot P2 will be S divided by 2. Because S usually is defined as P1 plus P2 squared. So it's 2 times P1 dot P2, so this I have to divide by 2. Same for T. And P1 dot P3, that is U divided by 2, but U is minus S minus T. And this is actually equal to U divided by 2. Okay. Next, I define the integral. So my propagators will be K square, K plus P1 square, K plus P1 plus P2 square, K plus P1 plus P2 plus P3 square. So that is the massless box integral. These are my 3 propagators. And my loops, my loop momentum is K. I have to tell the code which of these momenta is the loop momentum. I mean, I used for myself the convention that K is the loop momentum, P1, P2, P3 are the external ones, but of course the code doesn't know, so I have to tell it who is the loop momentum. And now I give this all to the code. So, well, this is just a name. So if I had more integrals I want to implement, you could distinguish them. I give it the list of propagators and give it the list of loop momenta. I ask it to generate the recursion relations, and then this essentially looks for like symmetries between between the news essentially. So that is, remember for the bubble, for example, we said the diagonal, you can flip it. Analyze sectors. This is just a command that allows you to figure out the regions where the integral is completely zero. Right? You remember, for example, the bubble integral. We said that it's always zero unless both exponents are positive. So this just tells the code, go and look for the regions where things are zero so that I don't need to care about them anymore. Yeah, so what will come out will be, it will always spit out these strings of zeros and ones, which essentially a 1 means that the exponent is positive. So you have a denominator. A 0 means that the exponent is negative. So for example, when it says the sector 1, 0, 1, 0, it means the region where nu1 is positive because there's a 1, the region where nu2 is negative or 0, that's what the 0 means. Nu3 is positive because the third entry is a 1, nu4 is negative or 0 because of the 0. So let's run that. Sorry, that's probably something. Let me start it again. I have to play with it. Yeah. So it produces some output. Never mind. So you can ask it, for example, what are these recursion relations? Well, they look a bit cryptic, but if you want, you can look at them. J always means that's the integral. Nu1, nu2, nu3, nu4, and then it gives you all possible recursion relations where you relate things, for example, to nu1 plus 1, nu3 plus 1, nu1 minus 1, and so on. So those are the recursion relations you find. There's 1, 2, 3, 4. There are 4, which is indeed what you need. Remember that the recursion relations are obtained by saying, well, it's dk mu, and then you have to put a vector v mu times something integrates to 0, where v here could be k, p1, p2, p3. So there are indeed 4 recursion relations that you can find. I can also ask is, okay, for which values of the exponents do I definitely know that the integrals are all 0? Well, for example, when all the exponents are negative, then the integral is scalars and it's 0, and you can check that there are other combinations where the integral is identically 0. Good. So now I've found the recursions. Now I can even ask the code to solve them. So let's run that. There's the syntax you need to look at the manual, but this essentially just solves the recursion relations. And it does it now sector by sector. So it first solves the recursion relations when nu1 is negative, nu2 is positive, nu3 is negative, nu4 is positive, and it says, I found a master. And it does it when nu1 is negative, is positive, nu2 is negative, nu3 positive, nu4 negative. It found a master, and it goes through all of them. For example, in the sector when nu1 is negative, all the others are positive, there's no master. That matches what we know, because remember, this would be something like a 3-point function. Nu1 is negative, so that propagator is absent. There are 3 propagators, but there was no master for this class of integrals that had 3 propagators. And indeed, the code says it doesn't find any master in this sector. And the same for all sectors where you have 3 propagators. It says master found none. This is a sector where you have all 4 propagators present, and it finds a master, which is the box with all unit powers of the propagators. So in the end, I can just look at what are the masters. And what you find is precisely the three masses that we had seen in the lecture. There's the box with 4 unit powers of the propagators and 2 bubbles in the S and in the teacher. And now I can give the code any other values for these 4 exponents and ask it to IBP reduce, and it will decompose that integral when u1 is equal to 2, u2 is equal to 3, u3 is equal to 1, u4 is equal to 1. It will decompose it into a linear combination of my 4 basis elements.
Can you explain again why the 3 propagators? You said this last time, but I missed, I think, the key point here about why they.
So you can in some, so there's 2 ways of explaining it. One is to say, well, if you didn't know it, that is the answer. If you run this machinery, it tells you that there is no well, this would be a 3-point function with one leg, one massive leg and 2 massless legs. So it would be like what you get like as a 1 loop diagram where you have a massive particle decaying into 2 massless ones with all propagators massless. That would be the kind of diagram. And it just turns out that the code here would tell you that, well, actually that's, well, let's look what it is. Maybe that is maybe more instructive. For example, you wanted a 3-point function. This would be 3-point function because 1 propagator is absent. And what do you get? You see that this thing is actually proportional to a 2-point function. So there is just no, the integral for 3-point function, all propagators are massless, and 2 external legs are also massless. It's just equal or proportional to a 2-point function. That is just what comes out mathematically. You can go for the mathematical origin, but say if you don't know it, the whole point of this machinery is that it allows you to reduce the integrals that you need to compute to an absolute minimum. So if you have such a, well, maybe you can also draw the diagram, maybe that makes it a bit cleaner. So yeah, maybe let's look at it very concretely. Imagine you wanted to compute this diagram. Let's say it's QCD. So these are all good ones. That's a 2-point function. This would be P1, P2, P3, P4. Another diagram that contributes to this process would be this one, with the same assignments for the momenta. But then, of course, I have others. I also have things like these. Right? That contributes to the same process. But the code will tell you that this is actually up to some constant equal to this. So, which is this guy here. So there's just a diagram, and by diagram I always mean integral that you need to compute. Okay, there may be different numerator factors and so on, tensor structures. I'm not talking about those. I'm just talking about the actual scalar integrals that you need to compute. This diagram here with the triangle is proportional to the bubble as an integral.
And that's because everything is massless.
Because everything is massless, yeah. That is for this particular setup where you have P1 square equals P2 square equals P3 square equals P4 square equals 0, and all propagators are massless. If you make things massive, then it's different. It's always, you fix the kinematics and then you run the machinery. Okay.
Thanks.
Good. More questions? Yeah, so that is what we just said as source diagrams. This would be the mathematical formula that corresponds to it. That the 3-point function is equal to the bubble for this particular kinematic setup where all external legs are 4 masses external legs and no massive problems. Good. So I have then my 3 master integrals, 2 bubbles in the box. Now I can compute the differential equation. So the code also has a way, this function dinf, which just computes the derivative with respect to an invariant. And the invariant is, for example, here P1 to P2. So let me compute the derivative of the box, which has exponents 1, 1, 1, 1, with respect to P1 to P2. And what you get is this. So you get, as expected, the result of a differential operator is just a linear combination of objects where you have shifted exponents. But if I have all integrals that have whatever exponents, all integrals of this type, I can write down as a linear combination of the 3 masters. So I can also ask the code, okay, take this linear combination and write it back in terms of the basis. And that is the linear combination. So the upshot is the derivative of the box with respect to P1 to P2 is equal to the box itself and a term proportional to a bubble. So I have obtained indeed a differential equation for the box. Be careful is more like a comment. To match our conventions, I will have to divide by 2 because this is derivatives with respect to P1 to P2, while in the lecture we always said derivatives with respect to S. And S is 2 times P1 to P2. So let's take my vector of masters, and I can also now compute the derivative of the vector of masters, which is this, with respect to P1 to P2. I divide by 2 because P1 to P2 is S divided by 2. And I ask the code to reduce it, and I do that for the derivative with respect to P1, P2, P2, P3, P1, P3. So this is the derivative of my vector of masters, the vector I, in this order. So the first element in this vector would be the derivative of this bubble. The second element, which is here, would be the derivative of this bubble. And the last entry is the derivative of the box. And that for derivatives with respect to all 3 invariants Pi to Pj. Remember that we had the scaling relation, which said that there are combinations of these differential operators that act trivially. In particular, the derivative with respect to S12 multiplied by S12, and S12 is 2 times P1 to P2, plus derivative with respect to S23 multiplied by 2 times P1, P2 to P3, so S23. The same for S13 should act trivially. And indeed it does. When you look at it, if you add them up in this way, you get back just the original vector multiplied by a number each time, which is nothing but the energy dimension of the integral. You can check that that is indeed the energy dimension of the integral. Well, now we still have to fold in that P1 to P2, P2 to P3, P1 to P3 are not independent, but S and T are independent, and U is minus S minus T. The change of variables were given in the lecture, so I can just plug them in. So derivative with respect to S should be derivative with respect to S12 minus derivative with respect to S13, and the same for T. That's what I get. The scaling relation should be S, derivative with respect to S, plus T, derivative with respect to T. Should act trivially. This is a good check that I'm doing the right thing, that I not did a mistake. Because if I, for example, if I put a plus sign here, that would be the wrong change of variable. Now you see this fails. So it's a strong check that I'm doing the right thing. And in the lecture, we also had this change of variable yesterday from ST to what we call sigma and X. Call it the relations here. The slides of yesterday's lecture should have been sent around, so you should have access to them to see the details of how the change of variables came about. So I can just compute them and change S to minus S, T is minus X times sigma. And we said yesterday in the lecture that actually derivatives back to sigma acts trivially. So because sigma just is, well, the dependence of the integral on sigma is just sigma to some power, which is what you see here. While the derivatives back to X is non-trivial. So let me then package it into this matrix. So what I'm doing is I'm just now package everything to a matrix. Say the dimension is 4 minus 2 epsilon. So this would be the matrix such that the derivative of this vector, which is my vector of masters, is equal to this matrix times this vector. This is my matrix. Okay, and you see, well, this is already in the form of the type, well, you see it's linear in epsilon already. This just comes out like this. In general, this would not be the case. In general, the epsilon dependence would be much more complicated. This comes out like this. I can, however, even make it a bit simpler. Well, because here you can even reach this canonical form where A1 is 0. So we can do a gauge transformation. So it's m minus 1 times A times m minus derivative spectrum of m. This is the formula we had in the lecture yesterday and also we recap today. And let me choose as m this simple matrix here. I'm just pulling it out of my head. So, for example, there are computer codes that allow you to find it. And also in the lecture tomorrow, we'll explain a bit how this comes about. So let me now do a gauge transformation of my original matrix with this m. And now you see, all of a sudden, this whole thing has become proportional to epsilon. Okay. So this would be the matrix in canonical form that you get for the differential equation satisfied by the vector of master integrals for the massless one loop box. Now, how do you solve it? Well, let you do it with this perturbative exponential. So let me just here, because it's easier to code it up, I just define an object where I can call the variable not x, but x something, x1, x2, x3, because I have to integrate over it. So I want to change the name. It is just the same as this matrix here. Okay. Okay, so let's look at the path-ordered exponential. So at leading order in epsilon, the path-ordered exponential is just the identity. And, well, so maybe let me, just before we go on, let me show you again what we're doing now, just to connect it to the discussion. I'm now unfolding this formula. So at leading order in epsilon, I get 1, and then I look at what kind of integrals I get to first order in epsilon, to second order in epsilon, and so on. Okay, I'm just unfolding this. And unfortunately, I cannot show you the two things back to back, but you can open the slides and you can see the formulas on the slides and what happens in mathematical code. So it's first order in epsilon, I just need to take the matrix and integrate it. And that's what I get. Now, here I just compute the primitive. I didn't care if I integrate from x0 to x. I didn't care too much. The reason is that changing x0 is just changing the initial condition, because that's the point where I start the integration. The important thing is that I manage to get the primitive right. And that is just the integral of a1, of a, which has 1 over x and 1 over 1 plus x, which gives me integrated log x and log of 1 plus x. At epsilon square, well, now I have to multiply two of these matrices in a specific order because it's path order. So first matrix, then the second matrix. And then I have to integrate the rightmost matrix, which depends on x2, up to x1. And then I have to integrate the rest in x1 up to my final point x. And this is what you get. Now you get also things like, well, you get logs, squares, but you also get dialogues and stuff like that. Third order in epsilon, I can continue like this. I have now 3 products of this matrix that come out of exponential, and I have to integrate along the path in an ordered way. So the rightmost object, which depends on x3, up to x2, and then x2 up to x1, and finally x1 up to x. And what you get is, well, this is what you get at the beginning. Then you integrate over x3, you integrate over x2. And finally, you get this matrix here, which now also has these 3 3s in there. And so this is the matrix, the path ordered exponential to third order in epsilon. And you can check that this indeed solves the differential equation. Now I can check it explicitly by just taking the general solution multiplied by this matrix. That should be the same as computing the derivative of the matrix. And indeed, to third order in epsilon, that is correct. And just to fold it up, well, to wrap it up, what I can do is I can now solve, I can also fix the initial condition. Well, let me cheat a bit in the bubble I know, because we had computed explicitly. So I know the bubble, there's a normalization factor for the bubble. There are certain factors like this factor, which were part of my matrix MM here. So those I don't need to include. So I just need to include this factor C gamma, which is this factor here. So my 2 bubbles are just C gamma in this normalization. And the box is something. I don't know what it is. It was normalized such that it starts at order epsilon 0. That is the discussion we had before. There's a pole, the massless box has a pole the type 1 of epsilon square, but I just absorbed that in my definition, and so I started at epsilon 0. So that is the vector which has initial conditions. So that's the, well, it always has this form. So I act with my general solution, which is the path ordered exponential on my vector of initial conditions. I get a horrible thing where we said the box must be such that for x equals -1, there's no singularity. You have to be a bit careful. You have to do analytic continuation right. We can discuss that maybe this afternoon. But the upshot is, if you do that, so there's a technical step that you need to do. You see that if you make a series expansion for x around -1 up to finite terms, the solution will in general contain things like log of 1 plus x, which shouldn't be there because there should be no log of 1 plus x. There should be no singularity as x becomes close to -1. That is what unitarity tells us. So you see, for example, well, let's go ahead and look at it order by order. In leading order in epsilon, there's no constraint. If I go to first order in epsilon, and I look at what is the coefficient of log 1 plus x, well, there is a non-zero coefficient. So I must choose C0 such that this term goes away because there should be no singularity as x goes to -1. So C0 must be 4. C1 I cannot constrain. If I go to order epsilon square, and I inject that I know now that C0 is equal to 4, well, you see that there's a log of 1 plus x unless C1 is 0. So C1 is also fixed. If I go to order epsilon cube and I inject what I know, then I see that the log 1 plus x goes away if C2 takes this special value. And if you plug that all in, so you plug in the values that you found, that is the solution for, this is one bubble, this would be another bubble, and this is the massless box. Now, with the correct normalization and everything, because I put back all the rotations that I made and so on, but this would be the solution of the differential equation with the correct initial condition. And you see, in order to fix the initial condition, I did not have to compute any value of the integral at any point. I just used the fact that physics tells me that there should be no singularity as u when u is equal to 0, which corresponds to x equals -1, and that was enough to fix the initial condition. And in many cases, that works like that. So just by using physical input, you can fix the initial condition. Okay. Good. I guess that's enough for this hour. So maybe we can take a 10-minute break. Let's maybe, since we also started a bit later, we can take maybe 10 minutes now and reconvene at 11:05. And of course, if you have questions, feel free to ask. Okay, if there are no questions, then let's reconvene in 10 minutes. So, the end of last lecture, we managed to compute the example of the massless box. Now, of course, it's a relatively simple example, but it shows essentially all the features of what you encounter in such a calculation. Now, the next point I want to address is the following. So, let's go back to what we did. So, now I guess you can see that from what you've seen in the Mathematica notebook, this form of the matrices dx over x and dx over 1 plus x is precisely the form that you get for the massless box. So this form was not coming out of nowhere. And you also see here from the way the calculation was organized that naturally in the epsilon expansion, what you get are iterated integrals. So that's just a very natural, the natural thing that you must get, okay? So you have, for example, here integrate from x0 to x and from x0 to t, and at second order epsilon, and so on and so forth. So at every order in epsilon, the fact that you have this differential equation in canonical form means that the solution at every order in epsilon will involve iterated integrals. And the number of integrations you will have to do at every order in epsilon will be precisely the order, well, the exponent of epsilon. For example, here you have the second order in epsilon, you have to do 2 integrals. So the natural thing that you get from these differential equations in canonical form are iterated integrals. So this means that iterated integrals are the natural language of the kind of analytic functions that you get for Feynman integrals. Now, it looks like here that this is what comes out of me having set up the calculation in this way, but it's actually much more general, because once I have finished the calculation, I don't know anymore how I did it, that I used this canonical form and it's part ordered exponential. The result is what it is, and the functions that show up in the answer are what they are. So the fact that I get these iterated integrals is essentially a general fact. So at every order in epsilon, I would have these iterated integrals. Those are the things that will show up. And so if you want to go on, you need to understand these iterated integrals. Now for the box, I just did it with Mathematica. I told Mathematica integrate, and it did the integrals all automatically. Like here, it gave me a log. At order epsilon square, it gave me a dialog, or error epsilon cube, it gave me this Lie3 function in addition. But it will not always be as easy. And in fact, even here, had I gone to order epsilon to fourth power, well, no, that would still have worked here. Epsilon to the fifth wouldn't, a Mathematicas integrate wouldn't have been able to compute the integrals anymore. You get new functions, you get new kinds of objects, which are iterated integrals, which are more general than the function Mathematica knows. And those are the objects that show up in multi-loop computation. So you need to understand them. So the natural question you can ask is, what is the simplest class of iterated integrals that you get from computing Feynman integrals? Okay. And so this will be the next part of the lecture. We'll now look at the simplest class of functions that you can get, and we'll try to understand their properties. And the reason for doing that is because those are the things that show up. So solving the differential equation in terms of iterated integrals is nice, but at the end of the day, you need to get numbers out. So you need to know how to evaluate these functions. You need to know how to analytically continue them, because these are functions that are multi-valued. They have branch cuts. You have to know how to continue them, how to make sure that the numerics is actually, well, you have a convergent way of getting the numerical values out. On top of that, we will see that by looking at these functions, there will be a lot of mathematical structure that pops up. So there's much more structure than you may naively think. And this is just the simplest family. So then you have more complicated families. We may, if we have time, look at those a bit on Friday. But it shows you already that for the simplest case, there's a lot of mathematical structure. And so what is the simplest family? Well, those are these polylogarithms. We had them in the very first lecture. So we can now go back to the definition, and you may look at the definition now with different eyes. So polylogarithms, or sometimes multiple polylogarithms, are defined by this identity. So it's a recursive definition. It's a function of n+1 variables called a1 to an and x. X is the upper integration limit, and the others are quantities that appear in the denominator. So it's this recursive definition. But as I guess you can see that if you unfold this recursion, then you get precisely the kind of iterated integrals that we had before. The reason is that here you see this guy is evaluated at t. So this guy here will be an integral from 0 to t. And then you get precisely this iterated integral structure. Okay. Now, there are some technical issues associated with this definition. When an, which is the last guy here, is equal to 0, then you can actually, well, if you look at the details, you would see that this integral diverges, because if an is 0 and the upper integration boundary here is 0, the integral would diverge. By convention, let us define this simply as the log. So in other words, this would mean that g0 x is log x. This would be something like the integral from 0 to x dt over t, in quotation marks, because you see that this integral is divergent, because dt over t, they cannot integrate it down to 0, but the definitions still make sense if you accept this definition. So this also shows that these polylogarithms contain the logarithm as a special case. I leave it to you as an exercise to show that they also contain the liens as special cases. What's sometimes called the classical polylogs. In contrast to the multiple ones, which are these G's. Okay. So that's the basic definition of a polylog. And I hope that now you understand better why those things show up. Those are precisely the kind of iterated integrals that showed up for the master's box. And I guess you can also see that the master's box was special because they just had one over x and 1 over 1 plus x. But in general, I could have other kinds of denominators and I would get these G's. Good. So what do we know about these functions? Well, the first thing is you can easily check, well, check, let's call a definition at this point. That there's a natural thing you could call invariant that you can attach to polylogs, which is, well, the number n of integrations. Right? So every polylog I can characterize, among other things, by the number of iterated integrations that I did. And let me call the number of such iterated integrations the weight. For example, log x has weight 1. If I have n iterated integration, I call it weight n, so that also ln has weight n. But I also postulate for now that this weight is additive. So if I multiply two objects that have weight 1, I get an object that has weight 2. It makes sense. If the weight counts the number of integrations, if I multiply two objects that have one integration each, I would expect that this corresponds to 2 integrations. So that's this natural kind of invariant you can attach to a polynomial. I will extend this, well, not I, that's it's mathematically acquired in the end. You will also extend this to numbers. For example, if I define log x to have a weight 1, well, then pi better have weight 1 as well, because pi, I can say, is the logarithm of -1. Depending on which branch of the logarithm I choose, I would be plus I pi or minus I pi, but the logarithm of -1 is proportional to pi. You may know that if you take the Duhr logarithm and you evaluate it at 1, you get pi squared over 6. And so you see that this definition actually makes sense. Because if pi has weight 1, pi squared should have weight 2. And the Duhr logarithm has weight 2. More generally, this more as a side comment that, well, we will need it later. The values of these liens at 1, there's something known mathematically as zeta values. They are called zeta n. It's the Riemann zeta function evaluated at n. And the other thing which I will do is I will define rational functions, rational numbers, as having weight 0. Now, for the experts, it's actually what I want here is algebraic rather than rational. But let's think of it as rational numbers or rational functions, as say, have weight 0. So at this point, that's the definition. It's nothing particularly deep. Good. So what do I know about these functions? They look pretty ad hoc at this point. So there's no reason why there should be any kind of deep mathematics behind it. Let's look at the first thing. Let me multiply two polynomials. For the sake of the example, let's multiply two objects that have weight 1. So an object that has weight 1 is an object of the type GAX. GAX is, for example, this interval here. Note that as a side comment, this is actually GAX is actually log 1 minus x divided by a, if a is not 0. So it's actually just a log. As long as it, well, unit a is 0. then I multiply two such objects together. So let's take gbx, which is given by this integral here. So I multiply them together. And well, I get an object of weight 2. Right? Two integrations, so I get the product as weight 2. So let me write it as an object of weight 2, where I have two integrations. I haven't done anything, and I've just used Forbini's theorem to combine these integrals into one double integral, a trivial one because of practicalness. With this integral now, we see that both integrations go from 0 to x. So this is actually an integral over a square. Okay? With a square with sides 0x. Right. 0x, and then what we see the 4 corners. The corners are 0, 0, 0x, xx, x0. But now let's do the following. Let's split, well, so I did this square. Let's split the square along the diagonal. Okay, so I can write the square as a sum of two triangles. Or rather, I can write the integral as sum of two integrals over these two triangles. And what you see is, for example, if you take the green one, the green triangle, that would be the one where you integrate from 0 to x, you know, in the t1 direction, and from 0 to t1 here, for example. And the other one would be you integrate from 0 to x here in t2, and from 0 to t2 in the x direction. Okay? So that is how I can split up my integral. And now you see I've obtained a sum of two terms, each of which has weight 2, and is actually an iterated integral. Each of these two integrals is an iterated integral, and actually each of these two integrals is a polynomial. So what I conclude is that if I multiply gax and gbx, I get gabx plus gbax, which looks, well, at first glance, pretty mysterious, pretty awesome as well. There seems to be some structure in there. Or maybe it was just an accident. Maybe the fact that these were just weight 1 was simple enough. But there's actually a structure behind it. It's called shuffle algebra. And to understand it, to see how this relation generalizes to general polylogs, well, let's interpret it as follows. Imagine I give you two decks of cards. One deck has one card, which I label with A, and the other deck has also one card, which I label B. So I have these two decks. Now let me shuffle the cards. Well, what are all the possible outcomes I could get? Well, since each deck only had one card, there are precisely two ways I can shuffle them. Either I put A on top of B, or I put B on top of A. Those are the only options that I have. Those are the only ways I can shuffle my two decks. And you see, that is precisely what the relation above tells me. So the way to multiply polylogs is essentially as easy as shuffling cards. That is why this algebra is called a shuffle algebra. It's the same mathematical structure. Multiplying polylogs or shuffling cards is the same algebraic structure. For example, what would happen if you have one deck of cards with one card labeled A, and the second deck has two cards labeled B and C in the order such that B is on top of C? Well, how can I shuffle these two decks? I have three possibilities. Either I put A on top of the second deck, so A is on top of B is on top of C, or I put A in the middle, or I put A on the bottom. Those are the only options that I have. And so what is the result of multiplying GAX and GBCX? Well, it will be GABCX, GBACX, and GBCAX. Note that I'm not allowed to switch the order between B and C because my deck was B on top of C. I'm not allowed to shuffle cards inside a deck. I'm just allowed to shuffle one deck into the other. Okay. And this is indeed an identity. This simple idea of shuffling cards is enough to work out what is the product of two polygons, which is quite amazing. Okay. Is that clear? Is there any questions about what the shuffle algebra is?
I have one question, which is not about the shuffle algebra, but do you have to worry about whether A or B lie within the region of integration, because then the denominator blows up?
Yeah, so that's a very good comment. I was sweeping that under the carpet because we will come back to discontinuities a bit later. But maybe just to put things into context. So here you see, well, let's maybe go here. So my polylog is defined in the following way. So what's happening here? I have the point 0 at the point x, and integrating from 0 to x. And somewhere there are these points A1, A2, A3, and so on. Now, of course, if A1 happens to be here, I'm in trouble. So what happens is, in that case, well, you would need to deform the contour. You would get something like this. But you would need to tell me what is the prescription. Do you do this or do you do that? Right? So then
or you could do principal value even, which would be a linear combination of the two, I guess.
Yeah, but here it turns out that you have to, I mean, you choose a path and you integrate along the path.
Okay.
Otherwise, some of the, like, for example, the shuffle algebra and things like this may not hold anymore. While if you choose the path and you indent the path, that is the mathematically correct way to do it. Everything else would be corollaries of that. So we will come back to that later on when we discuss discontinuities. For now, you can say whenever the integration variable lies on the path, I have to, well, doing this is equivalent to saying, so green here would mean that A1 is to interpret A1 minus I epsilon, while the lower indentation would be A1 is interpreted as A1 plus I epsilon. Okay. That is the other.
Which one do you use if you want the shuffle algebra relations to work?
Either one would work.
Oh, I see.
While if you do principal values, then you take differences. It works fine if you have, so either one would work as long as you use the same one everywhere, of course, okay? If you, whenever you see A1, you have to choose consistently A1 plus or minus I epsilon.
Mm-hmm.
While if you do principal value, it would work fine if you do this once, but if you have to do it for A1 and for A2 and for A3, you see, you would have different linear combinations with different weights. And then the shuffle algebra would not like that, because you would have one end of products of things which were linear combinations. It wouldn't like it. While as long as you do just this, indenting the path, or equivalently just giving small imaginary parts, that's fine. It's just that A1 was shifted slightly off, and then you're no longer in trouble and all the relations hold.
Okay, thanks.
But we will come back to discontinuities a bit later. That's why I didn't want to go into this now. But this is, of course, a very important point. More questions? Okay, so then let's go back to our polylogs. So polylogs form this shuffle algebra. The multiplication is given by the shuffle product. Note that it's implicit in what I wrote, but it's important that you have the same x in both factors. Why? Because this whole idea was that I get this square and I can split it along the diagonal. So I need this, well, it needed to be square, not a rectangle. So there is indeed some more algebraic structure. So these polylogs form an algebra. So let's formalize this a little bit. So the first property, which I think is obvious if you think about it, is that we had this invariant weight, which counts the number of integrations. Clearly, the multiplication of polylogs preserves the weight. Well, the weight was almost defined like this, but you see it explicitly from the shuffle algebra. You can also, if you want the analogy with the cards, I mean, shuffling cards does not change the number of cards. Okay, the number of cards in my deck is the weight. And if I shuffle 2 decks of cards, I get a new deck of cards, which has just the sum of the number of cards is equal to the sum of the cards in each deck. So multiplication preserves the weight, preserves the number of cards. So the weight is something very robust, and we'll actually see as we go along that the weight is really, it's something extremely robust. You cannot, if you have a certain weight, there's no way you can change it. That's essentially the message that will come on. But it only holds for polylogs, it would not hold for other objects. So let me define an to be, and let me call it in the following way. The mathematicians in the audience, just close your ears because I know that the sentence that's coming now is a bit ill-defined. That's why I put it in quotation marks. I define an to be the vector space of all polylogs of weight n. I think it's intuitively clear what I mean by this. It's a bit ill-defined mathematically because I didn't tell you what the AIs are, what is X, and so on. But let's do not go there. I think intuitively it's clear what I mean. Just allow all possible linear combinations of polylogs of a given weight, of a given fixed weight. And
just a fixed number of cards.
Yeah, but yes, that's what it is. But what makes it mathematically ill-defined is what X do I choose? Do I allow X to be, well, let me give you the concrete counterexample where things become ill-defined.
No, I wasn't going there. I was just going there, you know, that this just means it's a setup of 10 cards.
Yes, thanks. That's maybe a good way to put it. This would be things of the type 2 times this deck of cards plus 3 times this deck of cards. Is that what you mean?
Yeah.
Yeah,
But
so
there's
that's
another
the way
way
you
of
can think about it.
You have 9 and 4, that's 13 cards.
Yeah.
There's another way of distributing 13 cards.
Well, I'm just here looking at things of this type. So it would be like this, and then this, maybe this is C, D, E. This would be something like 2 times G, A, B, X,
okay.
plus 3 times G, C, D, E, X.
Yeah, so 5 cards, yeah.
5 cards, but this would be some, well, no, sorry, this is actually, sorry, this was stupid. Sorry, forget about it. This was stupid because this would be more like, I allow linear combinations of things that have the same number of cards, that have the same weight. So it would be more like this. This would be things like A, B, C, A prime, B prime, C prime. So this would be an object of the type 2 times G, A, B, C, X, plus 3 times G, A prime, B prime, C prime, X. Different decks, but in each deck, in the linear combination, there's the same number of cards.
Okay. Yeah.
And I allow the coefficients of my linear combination, I allow to be in Q. I don't allow for arbitrary complex or real scalars. The scalars are all rational numbers. And the scalars are weight 0. And those I denote by A0.
Can you generalize that to algebraic numbers?
Yeah, you can. Yeah. It would go through in the same way. It's just easier also for the notations. But you could also allow here, if you know the notation, I could write here Q bar, which would be the field of algebraic numbers. The distinction is actually things that are algebraic and things that are not, things that are transcendental. And that is where mathematically, if you dig, things get iffy, because if I write things like log x, that would be in general a transcendental number. But imagine I put x equals e, then this is 1, then it's a rational number. So I should look at things in the right way. So it should be, the distinction is linear combinations that are polylogs that are transcendental, and the scalars are algebraic numbers. Here, let's, for the sake of concreteness, stay with rational numbers. So I just allow linear combinations of polylogs with rational numbers as coefficients. That's what it is. So let me also introduce A without any subscript. I just take the direct sum of all of these vector spaces. So that is now, if you want, a vector space of all polylogs, of all possible weights. There would also allow linear combinations of decks of cards with different numbers of cards. There's a mathematical terminology that actually sums up this property of the multiplication preserving the weight. A is an algebra because A is a vector space and I have this multiplication. So it's an algebra. And this algebra is graded. Graded just means that if I multiply an object that has weight m and an object that has weight n, I get an object that has weight m plus n. So if you hear someone say that the algebra of polylogs is graded, that's what it means. So the number of cards in your deck is conserved when you shuffle the cards. Okay, is that setup clear? So far it was just a definition. I have an, which is, I allow linear combinations of polylogs of a certain weight. The coefficients, the scalars, are rational numbers, which are the objects of weight 0. I could use algebraic numbers if I want. And I take the direct sum of them. That gives me all possible linear combinations of all possible polylogs of whatever weight I like. That gives me an algebra. I can multiply them. And the algebra is graded because the multiplication preserves the weight. Okay? Good. Now comes the magic. No, it's not magic. Now there's more to be discovered. And yeah, let's go through this slowly, and then I think we stop for today, because this maybe for some people maybe that's maybe the toughest part. No. So let me first, before we go on, I guess everybody knows what an algebra is, right? An algebra is a vector space with multiplication. Let me give you another way of defining it, which will be useful to go on. So how can I think of my multiplication? My multiplication, I can think of it as a map that takes two elements of A and returns 1. Now this symbol here in the middle, this symbol here, which is this one, is called the tensor product. Now, I'm not going to go into the mathematics of what the tensor product is. There's a whole mathematics behind it. If you want, we can go through it during the discussion session. Think of it as pairs. For the sake of this discussion, it's good enough to think of it as pairs. So the elements of A tensor A are pairs of element of A. And my multiplication takes such a pair. So such a pair could be A tensor B. A and B would be elements of A. And my multiplication returns their product, which is A times B. Okay, that's a way to think about multiplication. Good. Why am I telling you that? Well, first of all, I can now go and have fun, and I can translate everything I know about algebras into this language. It's not particularly deep, but let's do it nonetheless. For example, I know that if I have an algebra, the product is associative. What does it mean? I take three objects. So I take an element, a triplet, ABC, out of A tensor A tensor A. And I can multiply together things in the first slot, not doing anything in the third. So I multiply together the first two slots. I don't do anything in the third, so I act with the identity. ID is the identity map. And I get an object in A tensor A, which is, well, I multiplied together the first slot. I didn't do anything in the third slot. Yes, I multiplied the first two slots. I didn't do anything in the third slot. And now I can also multiply together all three slots, and I get this. I get now AB multiplied together, multiplied by C. I could, of course, also first multiply together the last two slots. I would get BC and act with the identity in the first, not do anything. And then multiplying together would give me this. And our associativity tells me that these two things must be the same. Right? So I can phrase associativity as being, I draw the square and I can move around in the square, following the arrows in any way I like. You can either go around it this way or that way. I must get the same thing. Okay. So I'm just having fun and rephrasing everything in this language. The reason why this is useful is because now I can do other things. Now what I will do is I will reverse all the arrows. So instead of having something where I take two objects and I make one, I will take one object and make two. And I call this map a co-product. I will call it delta. So that a co-product is a map, a linear map actually, that allows you to take one object and break it into two. And such, well, if I have a vector space with co-product, it will be a co-algebra, just like a vector space with a product is an algebra. Whenever you see co attached to words in this context in algebra, it means that things go in the wrong direction. And instead of taking two, make one, that would be a product. You take one, make two, that's a co-product. And so with the same logic, there's also something called co-associativity, where now the logic is that you start from one object, and you can break it into two. And now, you see, once I have a rule to break one object into two, I can iterate that definition and break objects into three, into four, and so on. But I have two ways I could iterate the definition. I could either continue by breaking the first element into two, not doing something to the second, or break the second element into two and not do anything to the first. The co-associativity tells me that these two ways of iterating the definition should be the same. Just like associativity tells me if you have three objects, you can iteratively combine them and you always get the same thing. Co-associativity tells me your rule of breaking things into two can be iterated to a rule of breaking into three, four in a unique way. Okay? Does that make sense? This is maybe the most abstract part of the lecture. So If that doesn't make sense, please speak up. Okay. So I now have add two definitions. I had something called in algebra, a vector space with multiplication. There's something called a co-algebra, which is a vector space, which is co-multiplication or co-product. I can now even consider a vector space that had both a product and a co-product. And let me call this a Hopf algebra. Experts know that the Hopf algebra has some more axioms, but let's do not go there. So for me now here for the content of this lecture, it's enough to think of a Hopf algebra as being something which has an algebra structure, so a multiplication, and a co-algebra structure, a co-product. So I have both a rule to combine things and a rule to break things apart. And there's also some compatibility, namely this one, which, what does it mean? It means that if you first multiply things together and then you break them apart, it should be the same if you break A and B apart individually and then you multiply them together in the end.
Can I ask one question here? Is the breaking apart, are we assuming it's unique?
Sorry,
Are we assuming that the breaking apart is unique?
well, that is just like for multiplication, right? I may have more than one way of defining multiplication. I've not yet told you yet what is the rule delta. I'm just saying that I give you a rule delta to break things into two.
But is your rule a unique prescription?
Yeah, once I give you a delta, it's unique.
Okay, so it doesn't work on the integers, for instance, because you can take a composite number and have two ways of finding
Well,
factors.
we'll see examples of what delta can be later on. So that there will be a rule that I have to define, right? So,
Okay.
We'll see examples.
Okay, thanks.
One comment here, which is that you see here on the right-hand side of this equation here, I said I first break A and B apart, and then I multiply together the pieces. I have to tell you how to multiply the pieces. Now, this is more common for, well, the experts know this. There is a way to define a multiplication on pairs of objects, which is just component-wise. So I just take the first entries and I multiply them together, and I take the second entries and I multiply them together. And that is how multiplication of pieces works. It's more like a side comment in case you're not familiar with what a tensor product is. So, yeah, maybe to answer Howard's question. So let's look at an example. That will be the last thing we do today. And let's look at the following. So let's look at, as the vector space, we take for now all possible words. I allow linear combinations of words made out of certain letters. So words could be A, AB, AAB, and so on. You can also take again the analogy with the decks of cards. So a word A, B, C, A would be the deck of cards A, B, C, A. Okay, so you can take the same analogy. And they also allow things like 2 times this word, which will be 2 times this deck of cards. So it's just an abstract construction. And just like for the deck of cards, well, of course, the length of the word is like the number of cards in the deck, right? The number of letters. So let me define then AN to be all words of length n, or if you like the analogy with the decks of cards, this is all possible. Again, yeah, it's all possible linear combinations of decks of cards that have a certain number of cards. And well, if you take analogy with the decks of cards, then of course we know what multiplication is. It's the shuffle product. So I can now take deck with card A, multiply it with the deck BC in that order, and that is the formula that we've seen before. So how can I define a co-product in this space? Well, multiplication was shuffle, well, give me back all possible ways of shuffling the two decks. The co-product will be, I start from one deck, for example, the deck of cards ABC, give me back all possible pairs of breaking this deck into two decks. It's called deconcatenation sometimes. For example, how can I split the deck ABC into two decks? So either I say, I take A and the second deck is BC, or I take AB in one deck, the second deck is just a card C. And then there are also two other ways, which is just to say that the first deck is all the cards, but of course then the second deck is empty and I call that one. Or the first deck is empty and I put all the cards in the second deck. Mathematically also have to include those options, and if one of the two decks is empty. So deconcatenation is the co-product on my vector space of decks of cards. Just all possible ways of splitting the deck. Now, if these two operate together operator, I need this compatibility condition. So does it hold? Well, let's check it. So let's first check the left-hand side. And let's do all the steps. So I first do A times B. Well, this is shuffle. This is this. And so I have to compute all possible ways now of splitting this deck, which is here, and all possible ways of splitting this deck, which is here. And this is what I get. I'm clearly splitting the first deck AB. Either I split it into A and B, or one of the two decks must be empty. Right? And clearly the same for the other way. So that is what I get from the left-hand side. What if I do it the other way around? If I first split the decks, and then I multiply my pairs of decks together? Well, let me first split the deck. So how can I split the deck which is made of one card A? Well, clearly, if I only have one card, then the only way to split it is that one of the two decks is empty and the other one is the card. Right? That's all I can do. And the same for B. Let's multiply it out. And that's what I get. And to see what's going on, let's remember that multiplication is component-wise. So for example, if I just use distribution, so I would get this term times that term, I get 1a, 1b. It's component-wise, so this is 1ab, which is this term here. I could also have this guy. Then clearly with this component-wise, I would get A times 1 times B, which is this. And I guess you can see how all the other terms come about. Okay. And now to conclude, you have to remind yourself that it's in here, well, it's maybe sloppy in my notation. A times B here is the shuffle product. Multiplication is shuffle, so it's this. Same here. And now you can identify, if you do that, you can use the shuffle. Here AB is AB plus BA. AB is AB plus BA. if you do that, then you see that you just match all the terms. And you see that indeed this relation holds. So this operation of shuffling the decks of cards and splitting them is compatible in precisely the way that you need in order to get Hopf algebra. And actually, these two operations do define Hopf algebra. There are more axioms which one can also check with also. Okay. So I think this is a good place to stop. And I let you think a bit about Hopf algebras, but we can also discuss a bit more this afternoon in the discussion session. So thank you very much. Are there questions before we close the lecture for today?
Yeah, one quick one. I guess you've assumed that the distributive law works, which I guess is part of the definition of the algebra, right?
Yes, an algebra means it's a ring, right? It's a vector space with multiplication that makes it into a ring. So yes, there's a distributive law, and also assume that delta here is linear. Otherwise, for example, this wouldn't work.
Okay.
More questions? Okay, if not, then we can reconvene this afternoon at 2. If you have questions, to have a little discussion session, and otherwise we continue our exploration of polylogs and Hopf algebras tomorrow morning at 10 in the 4th lecture.